So here we got a hyperope with his or her far point behind the eye, and if we've done our job correctly, we've chosen a spectacle lens whose secondary focal point is at the far point. What that means is the image formed by the spectacle lens for a distant object will be formed at the secondary focal point, and that will become the object for the eye, and since it's at the far point, an image will be formed on the retina. Let's add a couple of other distances to our diagram, both starting from the center of rotation of the eye. The first one extends from the center of rotation of the eye, the COR, to the back vertex of the lens, and we call that D core. The second distance is just the difference between D core and the back focal length, and we can draw that as D core minus FB. And as we'll find out later, that represents the radius of curvature of the far point sphere. So let's remove a few of these items from the diagram and focus on the eye and the distances beginning from the center of rotation. So everything's well and good with the eye looking straight ahead through the optical center. We're measuring distances along the optical axis. But what happens when the eye looks up or down, or indeed left to right? Let's begin by turning the eye to look through the upper portion of the spectacle lens. And what I want you to see here is that the two distances, the two red arrows, maintain the same length. They are invariant. That's because the eye's far point doesn't change with the direction of gaze, and the distance, the original distance from the center of rotation to the back vertex of the spectacle lens doesn't change either. So let's bring the eye back down to the straight ahead position and now get the eye to look down through the lower portion of the spectacle lens. Again, the same thing happens. Those two distances are exactly the same. The only difference is that the end of those arrows representing the far point and the distance to the back vertex of the lens have moved. So now let's show those three directions of gaze on a single diagram. So what we have is three locations of the far point and three locations representing the rotation of the distance DOR. We could of course draw an infinite number of these lines, and what we would see is that the far point falls on a circle, or in 3 dimensions a sphere, and we also have a circle in front of the eye called the vertex sphere. We can get rid of those dots and we see two circles. The radius of the first is D core, and of course the radius of the second is the radius of the far point sphere, given by D core minus FB. So now let's remind ourselves that there's a spectacle involved here. It has a power FV, the back vertex power, and it has a secondary focal point F2. Now, in an ideal world, when the eye rotates and looks through different parts of the lens, the secondary focal point, or the image, would always fall on the far point sphere. But it doesn't, and there are two reasons for this. First, if we look at the area highlighted by the magnifying glass, we notice that the vertex sphere curves away from the back surface of this lens, and obviously the flatter the lens, the greater this discrepancy would be. This increased distance changes the effectivity of the lens. It's just like increasing the vertex distance for a regular spectacle lens when we're looking through the optical center. That increase in distance will give us increased plus power for the hyperopic correction, or decreased minus power for the myopic correction. So for this hyperopic correction, the effective focal point now lies in front of the far point sphere. Now we could show that for a range of directions of gaze, and we would get an image shell that in this example falls in front of the far point sphere. So in essence, the hyperope is overcorrected in all other fields of gaze. The second factor is that the effective power of a lens changes with the angle of incident light. So if the light strikes a lens at 90 degrees, i.e. the angle of incidence is 0, then the power is as specified. But if it strikes at any other angle, there will be some induced cylinder and some induced sphere. And we may have learned that already when we've discussed the effect of lens tilt on the effective power of a lens. It's just the same effect here. We're just considering peripheral rays or off-axis rays striking the lens as the eye looks in different positions of gaze. So one of the ramifications of this oblique incidence is we get some induced cylinder. And rather than having a single image shell associated with spherical rays, we now get two image shells associated with the two different arms of a power cross, or indeed the front and the back focal line. We call these two image shells the sagittal and the tangential shell. They represent two distinct powers, and in this diagram, of course, they deviate further from the far point sphere the further we go from the optic axis. At any angle of gaze or eye rotation, these sagittal and tangential shells have unique powers. So at any angle of rotation, there is a sagittal power and a tangential power. And of course, both increase the further the eye is rotated, or the more peripherally we look through the lens. The dioptric distance from the far point sphere to the sagittal shell is the sagittal error. Likewise, the distance from the far point sphere to the tangential shell is the tangential error. Now, as I said before, these two sagittal and tangential powers are just like the two arms of a power cross. So the difference between them represents the astigmatism. In this case, we call that the oblique astigmatism, or the oblique astigmatic error, or the radial astigmatism. They all mean the same thing. We can also think of a mean sphere, or a mean spherical equivalent, representing the average of the sagittal and the tangential powers. Now, the distance that this deviates from the far point sphere at any particular angle is called the mean oblique error, or the field curvature, or the mean power error. Again, all of those terms mean the same thing. So the cartoons we've been looking at thus far represent the actual curvatures in space of these various spherical surfaces. But in fact, it makes good sense at times when we're considering the sagittal and the tangential error, and indeed the amount of oblique astigmatism or the mean oblique error, to flatten these out such that the far point sphere is now a straight vertical line. We can go one step further and acknowledge the symmetry of these curves and end up with a diagram which we refer to as the field diagram. It is simply a plot showing the relationship between the rotation of the eye behind a spectacle lens and the sagittal and tangential errors. And of course, as you can see, these increased with increase in rotation. We could, of course, take things in the opposite direction. If presented with a field diagram, we could draw the mirror image of the lines below the horizontal axis, and then we could curve the far point sphere to take up a more meaningful form, representing a true sphere rather than a straight line. So we've looked at that for a hyperope. Let's do the same for a myope very quickly. For the myope, of course, the far point sphere is in front of the eye and therefore curves the other way. Just as before, its center of curvature is at the center of rotation of the eye. We could just as easily show the sagittal and the tangential shells, And to get to our field diagram, we just flatten out the far point sphere again to a vertical line. Finally, it's important to note that the tangential and sagittal shells could lie either side of the far point. On this final diagram, we've drawn them beyond or flatter than the far point sphere for the myope. So when we convert these to a field diagram, they lie on the left, representing negative error or undercorrection. Let's now take a slightly different angle on this and visualize what's going on from the point of view of the patient's eye. So here we've got a very young, handsome patient looking in various directions of gaze. Let's start off with the patient looking straight ahead. They're looking through the optical center, and of course at that location the back vertex power of the lens is just what we need. So in essence there is no sagittal or tangential error, so we can put zeros on both arms of the power cross. Let's now get the patient to look upwards, and we can put a circle on the lens indicating where they are fixating through the lens. Notice this is slightly above the pupil because of course the lens is slightly in front of the eye. And again we can draw the power cross and label them as the sagittal and tangential errors. In this case the sagittal error is the horizontal arm and the vertical arm of the power cross is the tangential error. We can make this more meaningful by assigning some actual dioptric values to these errors. So we've shown the sagittal error as -0.2 and the tangential error as -0.8. So the mean oblique error would be the average of these two numbers, which would be -0.5, and the oblique astigmatic error would be the difference between these two numbers, -0.6. Let's get our patient now to look off to the right, and the process is basically the same. They're looking at through a peripheral portion of the lens indicated by the dashed circle. Again, it's out beyond where the pupil appears to be for the reasons stated before. We can now draw the power cross and label it with the sagittal and the tangential errors. This time the tangential error is the horizontal line and the sagittal error is the vertical line because the eye is looking off to the right. The eye is looking horizontal. If you want to know how to remember these, the tangential error is the line pointing towards the pupil or pointing towards the optical center. Again, we could assign some powers to those, -0.8 for the tangential error, -0.2 for the sagittal error. So of course the oblique astigmatism would again be the difference, -0.6 or +0.6 depending on which way you want to specify it, and the mean oblique error would be -0.5.